The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Intermolecular forces. We'll once again begin here with a definition. It is the attractive interaction between molecules which can be due to hydrogen bonding, dipole-dipole interactions, London dispersion forces, or ion dipole forces. Simply put, it's going to be the force between molecules, and these are all the different ways it can take place, right? And let's begin here with hydrogen bonding and take a look at what hydrogen bonding is. We'll begin here once again with a definition. Hydrogen bonding. Hydrogen has a partial positive charge that has a charge attraction to atoms that are highly electronegative, that is oxygen, nitrogen, and fluorine, and to unshared pair of electrons on electronegative atoms. Hydrogen bond energies can amount to 40 kilojoules per mole. Wonderful. Looking here now at figure 4.3a, as we see water molecules, they exhibit hydrogen bonding, and just as we had stated in the previous slide, hydrogen is going to have a partial positive charge, and the oxygen, that's going to have a partial negative charge, right? Now, if we look here at figure 4.3b, we see with our ammonia here, we're going to have hydrogen bonding taking place as well between the partial positive charge of the hydrogen atom and the unshared pair of electrons on ammonia. And although we can't see them here, I'll just go ahead and I'll draw them in for us as such. Now, furthermore, this hydrogen atom here, because of the fact that it's so small and it doesn't have any electrons shielding its nucleus, right? When this hydrogen bonds with neighboring atoms that have an available pair of electrons, that bond is actually going to be quite strong. Furthermore, hydrogen bonding also has biological implications. Let's take a look at that now on the next slide here. Here we have in figure 4.4, we're looking at a picture of DNA here, right, where we have two nucleotide strands that are coiled around each other as such in a ladder-like structure. Now, it may not be apparent right away, but if we look very closely, we see that there's going to be hydrogen bonding that exists. That there is the hydrogen atom. Here we have hydrogen bonding, hydrogen bonding, hydrogen bonding, hydrogen bonding as such. And we'll talk a little bit more about this in the biology lectures, but I just wanted to introduce the notion to you now. Great, let's now continue to our next slide. Here we'll now take a look at dipole-dipole interactions, and let's once again begin with a definition. It is a force that can be either repulsive or attractive depending on the direction and placement of the molecules. The dipole force is small with an energy of 3 to 4 kilojoules per mole and is only impactful when molecules are in close proximity. Let's demonstrate that now. In figure 4.5a here we have polar molecules that pack very nicely, right, when they have non-like charges, right, that are in close proximity as such. However, when they have like charges that are in close proximity, they're going to repel one another. And the net force, right, the net force of these molecules is just going to be the sum of the attractive force and the sum of the repulsive force. Now, say we want to measure the strength of these dipole-dipole interactions. We can do so through what is known as the dipole moment, as it says here. And the dipole moment is just going to be the magnitude of the charge, right? The magnitude of the charge times the distance between the charges, And the SI unit for the dipole moment, as it says here, is going to be